Hello everyone, so today we are going to discuss normal distribution, standard or z-scores introduction, and 5-word problem and solution. For our key terms, normal distribution is a bell-shaped symmetrical distribution in which the mean, median, and mode are all equal. Z-scores, also known as the standard scores, the number of a standard deviation that a given raw score is above or below the mean. Standard normal distribution. A normal distribution represented in z-scores. The standard normal distribution always has a mean of 0 and a standard deviation of 1. Overview. What is a distribution? A distribution is an arrangement of value of a variable showing their observed or theoretical frequency of occurrence. A bell curve showing how the class did or our last exam would be an example of distribution. All distribution can be characterized by the following two dimensions. First, central tendency. What are the mean, median, and modes of distribution? Second, variability. All distributions have a variance and standard deviation. They also have a range and IR, but those are less important in differential statistics. The normal distribution and the standard deviation. When talking about the normal distribution, it's useful to think of the standard deviation as being step away from the mean. One step to the right or one step to the left is considered. Steps to the right are considered 3 standard deviation from the mean. 1 standard deviation away from the mean. 2 steps to the left and 2 steps to the right are considered 2 standard deviation away from the mean. Likewise, 3 steps to the left or 3 steps. The standard deviation of the data set is simply the number or distance that constitute a complete step away from the mean. Adding or subtracting the standard deviation from the mean tells us the scores that constitute a complete step. Below, I've put together a distribution with a mean of 58 and a standard deviation of 5. For example, if I add the standard deviation to the mean, I would get the score of 63 times 58. 5 is equals to 63. In stat terminology, we would say that a score of 63 falls exactly 1 standard deviation above the mean. Similarly, we could subtract the standard deviation from the mean. 58 minus 5 is equals to 53 to find the score that falls 1 standard deviation below the mean. Normal distributions are important due to Chebyshev theory, which states that for a normal distribution, a given standard deviation above and or below the mean will always account for the same amount of area under the curve. Let me explain. Take a look at the picture below. The shaded area represents the total area that falls between 1 standard deviation above and 1 standard deviation below the mean. Regardless of what a normal distribution looks like or how big or small the standard deviation is, approximately 68% of observation or 68% of the area under the curve will always fall within 2 standard deviation, one above and one below of the mean. Can you guess what proportion fall between the mean and just 1 standard deviation above it? If you guess 34, you would be familiar with 68 divided by 2 is equals to 34. Now, take a look at the next picture. It's basically the same as the first instant, only the time we're looking at 2 standard deviation above and below the mean. For a normal distribution, approximately 95% of the observation will fall within this area. The same thing holds true for our distribution with a mean of 58 and a standard deviation of 5. 68% of the data would be located between 53 and 63. Within this range are all of the data value located within our standard deviation above or below of the mean. Furthermore, 95% of the data would fall within 2 standard deviation of the mean, or in this case between 48 and 68. Finally, 99.7% of the data value would fall between 43 and 73, or within 3 standard deviation of the mean. The percentages mentioned here make up what some statisticians refer to as the 68%, 95%, 99.7% rule. This percentages remain the same for all normally distributed data. I've illustrated this principle in the graph below. Fun fact: the percentage of our distribution that fall in a given area is exactly the same as the probability that any single observation will fall in that area. In other words, we know that approximately 34% of our data will fall between the mean and one standard deviation above the mean. We can also say that a given observation has a 4% chance of falling between the mean and one standard deviation above the mean. Or, to put it another way, if you were to choose an observation or random from our distribution, there is a 34% chance that it would come from the area between the mean and one standard deviation above the mean. Next, let's talk about z-scores. Z-scores, which are sometimes called standard scores, represents the number of standard deviations a given raw score is above or below the mean. Sometimes it's helpful to think of z-scores as just another unit of measurement. If, for example, we were measuring time, we could express time in terms of seconds, minutes, hours, or days. Similarly, we could measure distance in terms of inches, feet, yards, or miles. We might have to do a little math to convert our data from one unit of measurement to another. But the thing we are measuring remains unexchanged. When we work with z-scores, we're basically converting our existence data into a new unit of measurement. Standard deviation unit, all interval or ratio data can be expressed as z-scores. We can convert any raw score in a z-score by using the following formula. Subtract the mean from the raw score and divide by the standard deviation. Let's go back to our distribution with a mean of 58 and a standard deviation of 5. We can convert 63, our raw score, into standard deviation unit, z-score, fairly easily. 63 minus 58 over 5 is equals to 5 over 5 is equals to 1. Just as 1 hour is equals to 60 minutes, our raw score of 63 in this distribution is equals to 1 standard deviation. The same holds true for observation below the mean. 53 minus 58 over 5 is equals to negative 5 over 5 is equals to negative 1. In this case, because our answer is negative, we know that 53 falls exactly 1 standard deviation below the mean. Now suppose we wanted to convert our mean 58 into a z-score. 58 minus 58, 5 is equals to 0 over 5 is equals to 0. When we convert our data into z-scores, the mean will always end up being 0. It is, after all, 0 step away from itself, and the standard deviation will always be 1. Data expressed in terms of z-scores are known as standard normal distribution, shown below in all its glory. We can also convert z-scores back to raw scores with the following formula. Problem number 1. We are interested in knowing how likely it is for one type of tree to grow to a certain length. The length of these trees exhibit normal distribution. The tree that you measure in 120 cm. Given the following information, do you think this tree length is uncommon? For this type of tree, the mean is 100, standard deviation is 10, and we have formula there. In order to solve this problem, we first need to understand what this distribution will look like. Remember that the standard normal distribution has the mean at the center with a z-score of 0. Below the image represents the mean and the distribution of the three heights. For now, we know that 120 cm is located to the right of 100 on the distribution. In order to find its exact location, we need to find the z-score of 120. Z minus score is equals to 120 minus 100 over 10 is equals to 2. The z-score is 2, which means that the height of 120 is 2 standard deviation above the mean height of 100. Next, we can find this z-score at z-table. This gives us the probability of 0.9700 72, which is very likely. Problem number 2. You are interested in how uniform the length of sacks are that are produced at the factory. You measure the distribution and see that there is a normal distribution for the length of the sack. Given the following information, how likely it is that the sack is above 25 cm. The mean is 20, standard deviation is 10.5. The formula is the same. Solution 2. This time, we want to know how likely it is for a sack to have a length and above 25 cm. This time, that we are looking for a right tail probability instead of a left tail probability, looking at the distribution will help you understand why. First, we find the z-score. Z is equals to score is equals to 20 minus 25 over 1.5 is equals to 3.33. Next, we look at the z-table to find the probability. This gives us the probability of 0.0004, which is highly unlikely.